Hey guys, in this video I'll be going over my reCAPTCHA solver code. So if you want to learn more about the concepts behind the code, like convolutional neural networks or transfer learning, you can click the link in the description to read my article about it. And if you just want to see the code, you can also click the link in the description and there will be a link to the code. With that being said, let's get started. In my model, I achieved an overall accuracy of 82% while using transfer learning with the VGG16 model. The first step was to declare imports. Something special I did was to load Google Drive. That's because I uploaded the dataset for Google Drive for ease of access. Here, I'm declaring the number of processes, declaring 20 samples per batch, and giving a 20% of the training set to use as validation. And this is where my data directly was stored. Something special about the transforms was I added the random rotation and the random horizontal flip. This is to make my model more invariant. What that means is that if I have a picture, for example, of an Iron Man, and he's always facing up, then the model will only know Iron Man if he's facing up. But if we add in random rotations and random horizontal flips like this, then the model will also be able to recognize Iron Man if he's rotated. And I also set the resize to 120 because that was the size of the pictures. Here I'm getting the data set, splitting it into testing and training, and obtaining the training indices for validation. And then I'm defining the validation and training samplers and preparing the data loader. Here I specified 5 classes: bicycle, bridge, bus, car, and traffic light. You'll notice that in the actual dataset from the GitHub over here, they have 11 classes. I decided to remove some of them because the VGG16 network was not trained on those. Therefore, we would not have any prior knowledge and we would have to be learning from scratch. And that would be a lot harder. Additionally, I had to balance the images because for some things, like the bus, which only had 800 pictures, and there were also some classes like the car, which had nearly 2,000 pictures. So I balanced the dataset to around 800 to 1,000 pictures per class. Here, I'm visualizing the training data. So this is just a function to help unnormalize and display an image. And I'm going through the data iterator to get a batch of training images, and I'm displaying them. So here you can see what the images look like. Some of these images are harder. Like here, there's cars, but there's also a bridge. And here again, there's 2 cars, but there's also a bridge. So it might be a bit hard for the model to work around these. And here's an image in even more detail. So this is what the computer actually sees. This is the red channel, green channel, and blue channel, and these should be filled with numbers between 0 and 1. Here I'm setting the device to use the GPU since it's faster, and I'm getting the pre-trained VGG16 model. And then I print the model architecture. So as you can see, this model uses convolutional neural networks through convolutional layers, ReLU activation functions, and max pooling. Additionally, there are adapted average pooling, and there's the classifier. So you might notice there are 1,000 output features. This is because the VGG16 model was trained on ImageNet, which has 14 million photos and 1,000 classes. But in our case, we only have 5 classes. Therefore, we have to create a new classifier. So first thing we do is to freeze the parameters. That's because these parameters are already trained in the VGG16 model and we don't want to be changing them. However, we do need to create a new classifier. So this part is the same as the original model. Here you can see 25,000 to 4,000, 4,000 to 4,000, and then 4,000 to 1,000. So this is the exact same, including the relus and the dropout. And then I just added one final fully connected layer that goes from 1,000 to 5. Now, this is probably not the greatest way to go about things, and I encourage you to play around with the architecture and see if you can get a higher accuracy. Additionally, I defined the loss function as cross-entropy loss, and I defined the optimizer as atom optimizer with a learning rate of 0.005. And again, these are some hyperparameters that you can tune to try and see if you can get a higher accuracy than what I got. Finally, we're moving the model to the device. Now, this is the training step. So I defined 15 epochs, and I kept track of the minimum validation loss. And here is pretty standard training, a training class. So we're keeping track of the training loss and the validation loss. we're setting the model to train. And then we're moving the tensors into the device, and we're clearing the gradients. Now we get the predicted value from the model, and then we calculate the loss, comparing the predicted values output to the actual target output. And then we backpropagate the loss and perform an optimization step. Finally, we update the training loss, and in my case, I updated the progress bar. And now we're on to the validation step. So the validation step is pretty similar to the training step. It's just that when we calculate the loss, we don't backpropagate through it, and we don't perform an optimization step. Instead, we just keep track of the validation loss. Finally, we calculate the average losses by dividing the total loss by the length, and then we print the statistics. Now, if the validation loss has decreased, then we'll save the model into model-augmented.pt. So here's what the training looked like. You can see that it took around 14 minutes or 10 minutes here per epic for 15 epics. And with that, and I think that's pretty short time considering the accuracy we got. So I'm quite happy with the model. And here, I think something went wrong, but we were still able to see the training loss and the validation loss. And you see that after the third epic, we were able to get the validation loss down to 0.6. And after that, most of the epics were not as useful. So I think if you trained it on less, you could probably get a similar accuracy. Now we're loading the model with the lowest validation loss, which we kept track of in the training. And now we move on to testing the model. So again, this is pretty similar to normal testing. So we're just keeping track of the test loss and per class. And we set the model to eval mode. And then again, this is similar to the validation step where we get the loss, but we don't backpropagate through the model. And instead, we just update the test loss. And here, we're converting the output probabilities to the predicted class and then comparing the predictions to the ground truth. So comparing the predictions to what they should be. And then we're updating the test accuracy for each class. Now we print out the average test loss and we print out the average test loss per class. Finally, we print out the overall test accuracy. So we were able to achieve a test loss of 0.69, and our test accuracy of bicycle, bridge, and bus were all around 90%, which is really good. Car kind of dragged it down a little bit, but I think overall it was really good, and traffic light was pretty average, and overall test accuracy was 82%, which I think is amazing. And now we visualize the test sample results. So again, we obtain one batch of images from the data iterator, we move the images to the device, and then here we're getting the predicted outputs and converting the output probabilities to the predicted class. And now we're plotting the images, and if it's correct, then we'll mark it with green, and if it's wrong, then we'll mark it with red. And you can see here, it was able to get 19 out of 20 images correct. And some of these images were really hard, like the one I got wrong, I can barely see the cars. So I think it's pretty good. And also this one, that had a car and a bicycle, but I was able to see that it was actually a bicycle. So I think the model was overall really good, and I'm really happy with the results. If you like this video, subscribe for more, and you can also follow me on Medium for more content. Thanks for watching.